Inference in first order logic. Sound inference. Find alpha such that KB entails alpha. Proof. Process in a search. Operators are inference rules. Example like modus ponens and B. This is an example of modus ponens. Alpha implies beta. We know alpha, we conclude beta. Here is another example. Ali at Al-Azhar, then Ali is okay. If Ali at Al-Azhar, then Ali is okay. We know Ali is at Al-Azhar, then we conclude that Ali is okay. This is modus ponens. Example. And introduction. This is and introduction. AI and introduction. If we have two sentences like alpha, beta, one sentence alpha and the second sentence is beta, we can combine them with and, like alpha and beta. Here is another example. Ali is okay. Ali has CS major. He is a major in computer science. We can combine both sentences in one sentence with and. Ali is okay and Ali is majoring in computer science. There is another example, universal elimination. Universal elimination, meaning we are going to cross out for all. If we have for all x alpha, we can replace any variable in alpha with tau. Here example, for all x, if x at Al-Azhar, then x okay. Now if we replace x with any constant like tau constant, we can use Ali. The sentence become Ali at Al-Azhar, then Ali is okay. So we don't need for all x. We replace for all x with every x, we replace it with Ali. So no need to write for all. Tau must be a ground term, i.e. no variables, must be a constant. Example, proof. We are given three sentences here. Bob is a buffalo. Bat is goat. Buffaloes outrun goat faster than goat. Okay, the first sentence, Bob is a buffalo. We can translate it to Buffalo Bob in first order logic. Then goat, bat. Bat is a goat. We translate it to goat, bat. Buffalo outruns goats, talking generally. For all x and for all y, if x is buffalo and y goat, then x faster than y. Outrun meaning faster. Okay. Now let's see what we can conclude here. We can use the rules in the previous slide, which is we can use an introduction, we can use universal elimination, we can use modus ponens to conclude things. Let's see. We can use between the first sentence and second one, use and introduction. Combine them in one sentence, meaning the fourth sentence become Buffalo Bob and Goat Bat. It's as simple as that. Then we can use universal elimination with sentence 3. Here we replace X with Bob and Y with Bet. It becomes Buffalo Bob and Goat Bet, then Faster Bob, Bet. This is the inverse elimination. Now we can use modus ponens between sentence 4 and 5. Modus ponens says if Bob is buffalo and Bet is goat, then Bob faster than Bet. And we know Bob is buffalo and Bet is goat. This is the condition. Then we conclude faster Bob and Bet. Faster than Bet. Okay, let me remind you with unification. In the prologue we talked about unification. A substitution sigma unifies atomic sentences B and Q if B sigma equal Q sigma. Let's see what it means. I have one column P and a second column Q, and we do the matching between them, substitution. Knows Ali X and knows Ali Ahmed. Here you see these are two equal names, the same thing. The first argument Ali with Ali, the same constant. The variable X takes the value Ahmed. X takes the value Ahmed. There is another example, knows Ali, Y, knows X, Ahmed. We talk about the same predicate here. Ali takes the variable X and Y takes the variable, Ahmed takes the variable Y. Here is X substituted with Ali, Y substituted with Ahmed. Knows Ali Y, knows X, mother of X. Here X takes the value Ali and Y takes the mother of Ali. We substituted X with Ali and Y with mother of Ali. Generalized modus ponens, G and B generalized. If we have let's see an example of it. It's not much. It says if B1 and B2 and Bn, where B1 and B2 and Bn goes to Q, where Bi sigma equal Bi sigma for all I. Example, P1 prime equal faster Bob Bet, P2 equal faster Bet Steve. P1 and P2 goes to Q, which means faster X and Y, and faster Y and Z goes to faster X, Z. And here we use X for Bob, Y for Bet, Z for Steve. The result would be faster Bob and Steve. Generalized modus ponens used with KB of definite clauses exactly one positive literal. Either a single atomic sentence or conjunction of atomic sentences goes to atomic sentence. All variables assumed universally quantified. Let's see forward chaining. Forward chaining. It's a way of inference and after we represent knowledge. When a new fact B is added to knowledge base for each rule such that B is unifies with premise. If the other premises are known, then add the conclusion to knowledge base and continue chaining forward. Chaining is data driven. It's called chaining. Also, forward chaining is called data driven. Example: inferring properties and categories from pair sets. A very simple forward chaining algorithm. Given m facts f1, f2 to fn, fm, and rules r1, r2, rn, repeat for I1 to n do. If one or more current fact matches the antecedent of R, then add the new fact or facts defined by the consequent. Flag the rule that has been fired. Increase them until no new facts have been produced. Let's see an example of forward chaining. Here is the first example, forward chaining. We are giving facts. Bob is buffalo, Pat is goat, Steve is a slug. And we are given rules. These rules, buffalo X and goat Y, then X is faster than Y. We have another rule, Y is goat and Z slug, then Y is faster than Z. And we have a third rule, says if X is faster than Y and Y is faster than Z, then X is faster than Z. This is a transitive relation. Transitive relation. We've seen it in discrete mathematics. It's called تعدي. Transitive relation. Okay, let's see how we are going to do the proof and what we are going to include. Here is, we do it like this. Step, have a column for working memory, things we do in memory. Rules can be fired, something called conflict set. Rules can be fired. Conflict set means if we have more than one rule that can be fired at the same time, it means we have a conflict set. Selected rule or fired rule. Which rule we selected to execute? Okay, in the beginning we put the fact here. We said we have buffalo, Bob is buffalo, Bat is goat, and slug is Steve. These the facts are given. So we take these facts and check which rule of the three rules the condition are satisfied. In the previous example, you will find R1 is satisfied and R2 is satisfied. So this is called a conflict set. We have two rules can be fired at the same time, and we can do that. So what we are going to do, we are going to take R1 and substitute X for Bob and Y for Bat. There is a T here. Okay, execute R1, the output of it, we have now from previously in memory, buffalo Bob, goat Bat, slug Steve. The new thing we got, faster Bob and Bat. Bob is faster than Bat. This is from firing rule 1. Okay, so we take the facts now here in memory and go test the three rules in the previous slide. Which one of them can be executed? Okay, after testing, we found that only rule 1 and 2 can be executed. We took rule 1 before, we don't take it again, so we take rule 2. We substitute Y for Bat and Z for Steve. Execute R2, the output of it. So this is old one. Buffalo Bob, Goat Bat, Slug Steve, Faster Bob was here, and Bat. The new thing is Faster Bat and Steve. Bat is faster than Steve. So we take these facts and test the three rules. Which one of them can be executed? We found that the three rules R1, R2, and R3 can be executed. We executed previously R1, R2, so we take now R3. But we are going to substitute X with Bob, Y with Bat, Z with Steve. So execute R3, the result of it, we have previously Buffalo Bob, Goat Bat, Slug Steve, Faster Bob, and Bat, Faster Bat, and Steve. The new one from R3, Rule 3, Faster Bob and Steve. Bob faster than Steve. Okay, take all the same thing, these facts, check which one of the rule can be executed. All of them can be executed, but we have executed R1, R2, and 3, so no more new rule can be executed, so we stop. This is called forward chaining. We start from the condition to the result. Okay. Another example for forward chaining. We are given facts A, B, C, and we have the rules A if A goes to D, if C and D goes to F, if F and B goes to Z. And we're given the goal, what we are looking for. Goal is Z. The goal is Z. The problem, does situation Z exist or not? We don't know. The first rule that fires is A goes to D because A is already in the database, knowledge base. Next, we infer D. Existence of C and D causes second rule to be fired, and as a consequence, F is inferred and placed in the database or knowledge base. This is in turn causes the third F and B goes to Z to fire, placing Z in the database. The technique is called forward chaining. Let's see it. Solve it step by step. Here it is. Step, work in memory, rules that can be fired, the conflict set, selected rule. 1. We put here in the memory the facts given, A, B, C. Then we take these facts, check the three rules, which one of them can be fired. The only one is fired is R1 because, as we said, A is in the facts. So we fire R1. The output of it, we have A, B, C, D is the new one. We take these facts, check the three rules, which one can be fired or selected or executed. We find R1 and R2. Since we took R1 before, we take R2. Execute R2, the output will be A, B, C, D, F. Take these facts, check the three rules, which one can be executed. We find all of them can be executed, R1, R2, R3. We select R3 because we took R1, R2 before. Execute R3, the output is A, B, C, D, F, and Z. Z, you remember, is the goal. So we check also again the facts against the three rules. We find the three rules can be fired. There is no new rule that can be fired, but at the same time we have found the goal Z. We stop. So, in forward chaining, rule 1, if the car overheats, then the car will stall. Rule 2, if the car stalls, then it will cost me money and I will be late getting home. Now, the question is, how do you arrive at conclusion that this situation will cost money and cause you to be late home? The condition that triggers the chain of events is the car overheat. Car overheat. If the car overheat is true, then we conclude the car will stall. And if we conclude car will stall, here it is, then the result, it will cost me money and I will be late getting home. Okay, the other inference method is called backward chaining. When a query Q is asked, if a matching fact Q is known, return the unifier for each rule whose consequent Q matches Q. Attempt to prove each premise of the rule by backward chaining. Some added complications is in keeping track of the unifiers. More complication help to avoid infinite loop. 2 version. Find any solution. Find all solution. Backward chaining is the basis for logic programming. Prolog. Remember Prolog, which we've seen in programming language. Prolog uses backward chaining. Prolog is a backward chaining logic program. Let's see an example. Backward chain example. The first example, we are giving the same previous examples and we've seen in forward chaining, same one. We are going to solve them by backward chaining. The facts given: Buffalo, Bob. Bob is buffalo. Bat is goat. Steve is slug. These are the facts. The rules are the same rules. If X is buffalo and Y is goat, then X is faster than Y. If Y is goat and Z is a slug, then Y faster than Z. If X is faster than Y and Y faster than Z, then X is faster than Z. This is a transitive relation. The goal is Bob faster than Steve. Why here we specified the goal in backward chaining, but in forward chaining we did not have this goal? Because backward chaining starts from the goal to the condition. If there is no goal specified, we cannot solve the problem using backward chaining. Clear now? Okay. Let's see how we're going to solve it. Well, remember, in backward we start from here, from the right to the left, backward. We start from faster, then we go to buffalo, goat. Faster this, we go to the left. We start from the right, go backward to the left. The same example, step 1, work in memory. We are given the facts. Bob is buffalo, Bat is goat, Steve is a slug, and we have faster Bob and Steve. From where did we get this one? This is the goal which we are asked to prove. We need to prove this goal. Bob is faster than Steve. That's why it's put here in the work in memory in the beginning. So in backward chaining we'll have the facts and the goal we need to prove. Okay, we take these facts and check on the right side of the rules in the output and the result. Which one contains any of these? We find first X and Z in the third rule. We find also faster Y and Z in second rule, and we find first X and Y in the first rule. So fast is found in the 3 rules in the right hand side of the three rules. So the three rules can be fired at the same time. We call this conflict set. So what we're going to do, let's choose R3. Since we talk about backward, start with the last one, R3. We substitute X with Bob and Z with Steve. Execute the rule R3. The result is, we have previously Bob is Buffalo, Bat is Goat, Slug is Steve, Faster Bob and Steve, and we have a new Faster Bob, Y, and Faster Y, Steve. This is what we get from firing rule 3. Y is not known. Y is not known. That's why we kept it Y for now. We take these facts, test the right hand side of the rules, the three rules, to see which one can be executed. All of them can be executed because all of them on the right hand side have faster. So we executed R3 before, we take R2 now. R2, if you remember the rule, says if Y is goat and Z is slug, then faster Y and slug. So we can substitute Z with Steve and Y with Bat, since rule 2 has Y with Bat. Hence, the value of Y can be replaced here with Bat. Y here can be replaced with Bat. When we execute rule 2, we get out of it goat, bat, and we have goat Y, and we have goat bat. It's a fact, so we don't add it again. And we have slug Steve. Slug Steve also is here as a fact, proved already. So here is the result. We have Buffalo Bob, Goat Bat, Slug Steve, Faster Bob with the Steve, Faster Bob with Bat, Faster Bat with the Steve. Now we take these facts, check the rules which can be fired. All of them can be fired. We executed R3 and R2. We execute now R1. Take into consideration X is Bob, Y is Bat. Execute R1. The result is we have Bob Buffalo. The rule 1 says if X is Buffalo and Y is Goat, then faster X and Y. So faster XY, X is Bob and Y is Bat, we get Buffalo Bob, which is a fact, and Goat Bat, which is a fact, meaning no more things need to be proved because everything is proved, and we stop in this case. So we prove this example by forward chaining and backward chaining. But remember, we had to have the goal specified in the beginning. Let's see another example for backward chaining. Here is example. Rule 1, if the car is not tuned and the battery is weak, then not enough current will reach the starter. Rule 2, if not enough current reach the starter, then the car will not start. Given facts, the car is not tuned, the battery is weak. Now the question is, how would you arrive at the condition that have resulted in the car failing to start? We check in the right hand side here from rule 1 and rule 2. taken in consideration the facts. We have facts: the car is not tuned, the battery is not weak, the battery is weak. So, and the fact says what resulted in car failing to start. The car failing to start, car will not start here in the rule 2, here is at the right. So when we execute it, it will give me not enough current reach the starter. This is our new goal. Not enough current reaches the starter. Where is that on the right hand side of the rules? It is in the right hand side of the first rule. Here it is. Not enough current reach the starter. So we execute it, we get the car is not tuned and battery is weak. And we know these two are given facts. The car is not tuned and the battery is weak. So we prove that car will not start. Backward chaining. Let's see a third example, like in forward chaining, and solve it in backward chaining. Here it is, the third example. We have the facts A, B, C. The rules: if A goes to D, if C and D, then F. If F and B, then Z. The goal is specified as Z. Now, first step, we have given facts A, B, C, and the goal Z. Remember, in backward chaining, we put the goal also. Rules that can be fired, the conflict set, and selected rule. So we take the A, B, C, and Z, and we look at the right-hand side of the rules. Right-hand side of the rules. Where do we have A, B, C, Z? We have Z in the third rule. Here it is. But we don't have A, B, C in the right here. Just Z in the third rule. Here it is. So the only rule that can be fired here is R3. Here is R3. So we fire R3. What is the result? We are going to get result F and B to be added here. F and B. A already here, B already here, C, Z, here is F. This is the new thing, is F. B is already fact. So, okay, we'll take here these facts and compare the right-hand side of each rule of the three to see which can be fired. Z can be fired. F, here it is also, we found F, can be fired, but D cannot be fired yet. So we have two rules that can be fired, R2 and R3. We took R3 before, so we fire R2. Fire R2, the result is C and D. Old A, old B, old C, Z old, F is old, but the new thing is D, because C is a fact here. So we take now, we take all the facts here and compare the three rules. The right hand side, here is D, F, Z. Which one of them is found here? We find Z is his third rule, and F in second rule, and D in the first rule. We executed R3 and R2 before, so we now take R1. Here is take R1. Executed, the result is A. A is a fact. Here it is. So there is no more things to be executed, and we stop because we proved Z, meaning we proved Z from result to condition. Here is a question: what is the difference between backward chaining and forward chaining in terms of cases in which they are used? The answer here, backward chaining is usually used when we can start with something we want to prove. Backward chaining, we start with goal, the thing we need to prove. Find implication sentences that would allow us to conclude it, and then attempt to establish their premises in turn. It is good when backward chaining factor is large, branching factor is large. If the branching factor of the tree, the node goes out with many factors, many branches, it's good to use backward chaining. And if we have little data, given facts, little facts are given, it's also good to use backward chaining and easy to identify the goal. This is very important. We said if the goals cannot be identified easily, we cannot use backward chaining. So when do we use backward chaining? When we have branching factor is large, little fact is given, and easy to identify the goal. But in terms of forward chaining, forward chaining is usually used when a new fact is added to the knowledge base and we want to generate its consequences. It is good when branching factor is small. See, the opposite of backward chaining. If the branching factor is small, and the second thing, most of the data are given, and many goals exist. Is it possible to have many rules that give the same goal? Yes, of course. In this case, we use forward chaining because it's very difficult for backward chaining with which goal to start with. If the goal is not easy identified, we use forward chaining. So, in short, forward chaining, if the branching factor is small and most of the facts are given and the goal, there are many goals, the goal is difficult to identify, we use forward chaining. However, backward chaining, if the branching factor is large, data given is little, not much data given, no much facts, and the goal is easily identified. The goal is easily identified. In this case, we use backward chaining. Again, a goal is easy to identify, meaning sometimes we have many goals. If you have many goals, meaning backward chaining cannot be used. And this way, we will use forward chaining. I think it's now clear the difference between forward chaining and backward chaining.